recording. There we go. It's such a tiny red dot. I never notice it when it's on, and so when it's off, I never notice it either. But you guys keep me on task. Thank you. Excuse me. Oh, boy. One second. Yeah. So, like I was saying, with business, you're going to have one graph that describes the cost of producing an item. You might have another graph that describes the cost of producing many, many, many of them. And so this point in the middle would be, let's see, so this is cost to produce an item. This is cost to produce bulk items, meaning you're going to make a whole bunch of them. And right here, this is the number of items where it makes sense. When I say makes sense, it's cheaper to order lots of them. Kind of like this. If you're buying something online and it says after the first 10 items, the cost changes and it usually gets cheaper, that's what this is. So that's a business thing. That's a manufacturing thing. Let me put manufacturing here. So this is why we care about this topic. If you don't care about it, that's fine. Just get good enough at it so you don't have to do it again. There, let me go like that. Nope, that's not going to work. I'm not at my normal desk. I'm still in Washington, so I'm trying to keep things visible here and not suck. Okay. So now that we're talking about how it's useful, let's talk about how we can actually use it. So I would say choose the method to solve that makes sense for the problem. I mean, really now. So if you're graphing, then you obviously want a visual representation. You want to see what's going on. That's why it's great in business. Most business people, they just want to see what's going on. They just want to see, oh, okay, the number goes up, that's a good thing. Unless it's money that they're paying, and then it's a bad thing. Nobody likes to pay lots of money. So this is purely based on application, when you really want a visual representation of it. For substitution or elimination, I was talking with a student this morning, and he really summed up when to choose which one of these. He said, choose the method that is the least amount of steps. That's it. Just pick whichever one makes the problem easier. If you're going to do substitution, okay, it's easier than doing multiple steps to make it work for elimination. If the problem starts out easy to cancel, okay, use elimination. So I'm going to add one more thing to this. I'm going to say whatever makes it easier. So just keep it simple. So let's do an example of this. And I'm gonna make your day. It's all word problems. So let's do practice problem 1. It's called a break-even point. And a break-even point is very important if you ever want to own your own business. Excuse me. And that's when you officially made enough money to pay for your project And all money after that is that sweet, sweet profit. Profit is the money you make. So the break-even point is kind of beautiful. You want a low break-even point, but it'll be whatever it'll be depending on your business. And everything after that is great. So a fashion designer makes and sells hats. So we're making and selling hats. Anytime you make something, it costs money to buy materials and to pay your workers to make it. So we're making and selling hats. I don't know. Feel free to picture like funny hats for people to wear at the Ministry of Silly Walks, something like that. The material for each hat costs $5.50. So material cost is $5.50 per hat. The hat sells, so the sale price is $12.50 per hat. That's pretty cheap for a hat. A good hat, well, that could be a lot more than $12.50. Maybe change that into a comma and move it to the left one. That's for like a super nice hat, the kind of hat they bury you with. All right, the designer spends $1,400 on advertising. So we have advertising because no one will buy a hat if they don't know it exists. And that's $1,400. Now, I'm going to put signs in here. We're gaining $12.50 per hat, but we're losing $5.50 per hat because of how much money it costs to get the materials for it. So it wants to know what's the break-even point. So the first thing we're going to do is we need to break this out into expense and income. So the cost of it, the expense, is going to be Y equals 5.5 plus 1,400. So this is how much it's all going to cost. And the income, that's how much you're making from it, is Y equals 12.5x. Oh, that should say x there. Now here's the thing. I put a negative here for a reason. It's to remember that this costs us money. Okay, so remember, we're decreasing by that amount. So we have these two equations, and it looks like, honestly, substitution is the easiest one to manage. So when we substitute, what we're doing is we're going to say, all right, this is our income. I'm going to move it over here. So I have 12x equals 5.5x plus 1,400. That makes sense. And the next thing we're going to do is we're going to simplify this. And because it's a real world issue, you can leave it as a decimal. Decimals are okay for real world things. If it's pure math, try to avoid it because it's easier to deal with fractions. But for real world things, it's fine. So we're going to subtract 5.5x from both sides. And we're going to end up with an error. See, 12.5 and I wrote 12. If you catch me before I do that, or before I move on to the next step, or before I fix it, you get an extra credit point. So be very careful. So I'm going to subtract that from each side. So now I'm going to have 7x equals 1,400. And then I can divide by 7. And so x equals 200. And that's hats. So really, with the amount of money they've paid to buy the materials and to advertise, they have to sell 200 hats before they start to make money. And here's the thing. $1,400 does not get you very much advertising. It really doesn't. So scale that up. Think about all the TV commercials you see and the millions of dollars that costs. Well, if it costs, say, a couple $1,000,000 for a Super Bowl ad, how many hats would they have to sell to make it worth it? So it's a lot, but that's one way to solve this. Another way to solve it is going to use our negative here in a more traditional way. So what we're looking at is our income, 12.50, well, 12.5x plus 5. So this is positive because it's income, minus 5.5x, because this is negative, it's how much we're paying. Let's see, minus 1,400 equals 0. So here's what this means. This is our income. This is our cost. And these are both per hat. This is just a fee, and we're taking it away from our overall income because it's negative. We had to pay that. And 0 means it's break even. Meaning this is our profit so far. So if our profit is 0 and not negative, it's our break-even point. This is where we've earned as much money as it took to pay for everything. So this is another way to write the equation that might be a little more intuitive for you. I know it's not a 2 equation to unknown thing like this. This said our expense is 5.5x plus 1,400. Our income is 12.5x, and then we put them together. Well, that's nice, but this works too, and honestly, I think this works a little better. But it depends on how you think about it. So with these word problems, this is one solution. This is another solution. And of course, you would solve. And it's up to you to figure out which way you want to use to solve it. Sometimes you have to use 2 equations. Sometimes you don't. So it's going slow and being methodical. Any questions on this one?
No, Ms. Crockett.
No.
Okay. So with money, the cool thing you can do is you can go negative. I say the cool thing. It's not cool to go negative in money. But you can. So there's not really any limits on this. But that's not true for everything. In some real-world situations, we're going to have hard limits on materials. So other than money and certain other things, counting numbers like the number of gallons or liters in something, just as an example. I'm going to put example up here. Never go negative. Like, if you think about it this way, when you have a fish tank, you could have 0 water in it or some positive amount of water, but you're never going to have negative water because that's just weird. Like, yes, my fish tank can have negative 6 liters in it. Meanwhile, your fish are looking at you like, really, dude? Really? It's very strange. So you wouldn't measure it in negative. So if we're looking at a local zoo, we're filling 2 water tanks for the elephants. Elephants like to have water not only to drink, but also to help cool them down. So in this next example, we have 2 tanks of water for the oliphants. If you haven't read Lord of the Rings, never mind. Okay, 2 elephants. 1 tank contains 50 gallons of water. So I'm going to say tank 1, and I'm going to say tank 2. Because it's just easy to keep track of things this way. So tank 1 is going to fill at a constant rate of 10 gallons per hour. So increase 10 gallons per hour. And a gallon, I want to say, is something like 1.7 liters. I mean, correct me if I'm wrong, but it seems like something like that. I wonder if my notebook has it. Anyway. The second water tank, oh, and it's a 50-gallon max. The second water tank is 29-gallon max, so I'm just going to keep everything organized. So it's much smaller. And it fills at 3 gallons per hour. Okay. And so when will the two tanks have the same amount of water? H2O is how you write water in chemistry. So I'm going to write water as H2O. So when do they have the same amount of water? Well, that's what we're talking about, amount of water. So I'm going to say let Y equal the amount of water. And then I'm going to write my two equations. Oh, no, I misread this. So this one has 50 gallons already. See, this is why it's important to reread the question. This is 50 gallons already. This one has 29 gallons already. So they're partially filled. They like this tank a lot. And they've slopped most of the water out of it. This one still has 50 gallons of water in it. So Y equals the amount of water. So in our first equation, I have Y equals 10 gallons times X. So I'll say X is the number of hours. Because if you've ever filled a swimming pool before, you know it can take a while. Because you've got just one hose and you're pumping water into the pool, and it can take a while to fill it up. So X is the number of hours, so 10X plus 50. And our second equation is going to be 3X plus 29. So when we do this, I'm going to go ahead and solve. So this is my system right here. And when I'm looking at this, the easiest way to solve it is substitution. The reason why is 10x and 3x. There's no good way to make those the same number. Y is actually already just itself. So if you wanted to do elimination, you could. You don't have to, but you could. Or substitute, which is just as easy. It doesn't make any difference. I'm going to substitute because I can. So I'm going to substitute because this Y equals this one. I'm going to replace this Y with this number. So now I have 3x plus 29 equals 10x plus 50. That's cool. So far, so good. I want to get all my x's on one side, so I'm going to subtract 10x from each side. And so now I have negative 7x. That negative makes me nervous. Does not make me happy. Plus 29 equals 50. Subtract 29. And so I got negative 7x equals 21. I don't like it. Negatives are bad when real world problems. Divide each side by negative 7, and now I have x equals negative 3. What the heck even? If x equals negative 3, your book example keeps going with this and plugs it in and solves for y and all that good stuff. But x equals negative 3 means negative 3 hours. I'm going to say no time travel is allowed. So no time travel, no solution. You can't have negative time. It's just not possible. When you get into the high enough level math where you can have negative time, This is not a math problem you would be solving anymore. You would be working on the mysteries of the universe. So no time travel. And so you have to use your brain. Does it make sense to have -3 hours? No way. And then look at the problem and ask yourself, this tank fills really fast. It fills more than 3 times faster than this tank. This tank also had a lot more water in it to start. This one had less. So not only is this tank more empty, it fills slower. There's no way these two tanks had the same amount of water at any point, unless they were both empty or both full. But it doesn't say anything about that. So this, no solution. Does that make sense?
Yeah.
Okay. Hey, welcome. Let's see. Welcome, kiddo. I hope you're feeling better.
Hello?
Hey there. Can you hear me okay?
Yeah, I can hear you.
Good. All
I'm
right.
not feeling the best, but I'm gonna try to do as much of class as I can.
Yeah, well, you know what? Put your health first. I am recording this, so you can come back and watch the video when you feel better too.
Okay.
So, yeah, you didn't miss any notes. I went over problem 43, but that was from the last homework, and you're always welcome to come to office hours. It's all good.
Okay. Thank you.
All right. And really what we're doing today is seeing how these systems of equations make a difference in real world situations. So here with this problem, we solved it. We were looking at 2 big water tanks at the zoo. And one tank was filling very quickly at 10 gallons per hour, and it already had 50 gallons of water in it. The second tank had 3 gallons per hour of fill rate, so it's filling real slow. This one's like a hose, and this one's from like, I don't know, a giant pipe. And this one had even less water in it already. So this one fills slowly and had less water. And the question was, when are they going to have the same amount of water in them? Well, we set it up because we have y can equal the amount of water and x is the amount of time. Anytime you have a unit rate like this, time is almost always going to be your denominator. And we set up our system of equations. So the amount of water is equal to 3 times x, which is the number of hours we're filling that thing, plus the water it had in it already. And for tank number 1, the fill rate was 10 gallons per hour times x plus 50, which it already had. Solve them and you get x equals -3, which in regular algebra would be fine. It's a line. This isn't regular algebra though. This is describing a real world situation. So when x equals -3 and x is the number of hours, that means -3 hours. So since we're not allowing time travel, this means no solution for this problem. That's kind of my super quick explanation. The video has the full explanation though. All right, let us do another example. And let's see. This has a needless amount of vocabulary that's not really relevant to the class. Are they going to deal with other problems like this? It's kind of a stupid question. The next example your book has is very complicated, and I'm not really sure it's worth it to do it. I might do a problem off of your homework. Yeah, I'm going to do one of the boat problems because you've got a boat problem on your homework. All right. So I'm going to do 24 here for the next example. It's not off the homework directly, but there is another boat problem that is a homework problem. So we have a boat traveling in a river. Boat in river. I like it. I like water. With a current that has a speed of 1.5 kilometer per hour. Okay, so the river current and this is good vocab word to have. Current is the speed of the water. The speed of flowing water. So the river current is equal to 1.5 kilometers per hour. So it's a nice lazy kind of river. In 1 hour, the boat can travel twice the distance downstream that it can travel upstream. So I'm going to write that down. So boat travels twice the distance downstream. Now downstream means in the direction of the current. So it flows with the river. Then upstream. Let's see. So here's what that means in a meaningful sense. When you have a boat traveling this way, this is actually some physics too. We've got one vector describing the speed of the water, and then we're going to have another vector describing the boat, B. Now, when we go upstream, we're going to go double the distance compared to going downstream. So when we're solving this, what we're going to have is a boat that's traveling upstream. So this is going down. And this one, the boat's going up, and this is going down. And this is 1.5 kilometers. Now, it would be very, very tempting to say, oh, the boat, it's going double the distance. It must be double this. Don't do that. Just because the boat is going twice the distance down as it is up means against the current, you have to really read it. The boat still travels upstream. It still travels up. So if the boat matched it, so if this was 1.5 kilometers per hour going down, and this was 1.5 kilometers going up, well, they would balance out and the boat would go nowhere. So that doesn't work. So I'm going to say let D equals distance traveled. And so our distance traveled going downstream, D equals 2x. Upstream, upstream, that's still the same column, is just going to be D equals x. So that's our distance. But distance is a function of more than just how far it went. So it's twice that distance. Now we also need speed per hour. So the velocity of the boat, so like, how do I phrase this? The distance the boat travels is going to be equal to the speed of the boat. So we'll let, let's say, the speed of the boat, y, times time, minus 1.5 kilometers per hour times time. And that's our distance. And that's also equal to 2x. So 2x equals y minus 1.5 times t. It should look an awful lot like physics, because it is. Now, the problem tells us that we do this in 1 hour. Just 1 hour. So if t equals 1, I'm going to be able to say 2x equals the speed of the boat, y minus 1.5 t. Oh, I did something funky. So downstream, we add these because they're in the same direction. That should be plus that, plus that, plus that. minus 1.5t would be for this one. We have this. So now I have 2x equals y plus 1.5. Okay, so this is our first equation. This is the downstream working with the current equation. For upstream, my distance is just x. And so my distance is going to be a function where x equals y minus 1.5, because t is still 1, so y times time, and 1.5t, time is 1. So I have x equals y minus 1.5. Does that make sense so far?
Yes.
Okay. So x is the distance, y is the speed of the boat, t is the time, and 1.5 is the speed of the current, which in this case, we're working against it, so it's negative. So here's my second equation. I'm going to put the two together. So I have 2x equals y plus 1.5, and x equals y minus 1.5. This is a pretty nice elimination problem. So I'm going to subtract the second equation here. I'm going to say 2x minus x is just x. Y minus y is 0. 1.5 minus minus negative 1.5 equals 3. And so x should be 3 kilometers per hour. And then I'm going to check that. I'm going to take that 3 and I'm going to plug it back in, because 3x is, 3 is just kilometers. So now I'm going to take that and plug it back in. We want y. Y is the speed of the boat, because that's what we actually want. So x equals 3. So now I'm just going to use any one of these equations, really. I have 2x. So 2x equals y plus 1.5. 2 times 3 equals y plus 1.5. 6 equals y plus 1.5. And I know I say decimals are terrible, but this is a real world situation, so use decimals, that's fine. In pure math, you really don't want to do that, because it's easier to simplify without decimals. So I'm going to subtract 1.5 on each side, and then I get 4.5 kilometers per hour equals y. And because I have the teacher's edition of the book in front of me, I know for a fact that's the answer. So this is how you would do it. Now, is it long and drawn out? Yes. It's super helpful to have a drawing. This reminded me that my speed is going to be added to because the water is pushing the boat in addition to the boat pushing itself. This one reminded me that the boat is fighting the water, and it's harder to swim upstream. It's harder for the boat to move against the current. So when the water is still, this is my speed. If the water is not still, so the water is flowing, then this is the equation here that describes the rate of the boat with the current. This is the rate of the boat against it. So you just got to take your time. Your homework is posted. I did something a little different today. I've only got 2 kids in the evening class. I'm going to try combining the homework posts. So instead of having A block and B block, I'm going to have A and B together, so everyone can access the same file and I don't have to list it twice and nobody has to figure out which one they're allowed to access. So the one that says your homework is 6.4, do that one. Now your homework, or chapter 6.4, and I know we're over time, but your homework for 6.4, I know I paused it, 1 second, is there we go, is right here. You're going to do 7 to 27 odds, and 28 to 37 all. I did it odds because there's a lot of word problems, and you can see they take a lot of space. So 28 technically says it's a challenge problem. It's not. You guys have already solved problems like it on normal homeworks before. So it just says it's a challenge problem because it's being fancy. It's not actually that bad. And then 29 to 37, those are all review from earlier sections. So we're about halfway through the chapter. I want to say this chapter has 7 sections in it. And Monday we're going to start something really different from what we've been doing. So I want to see how everyone is doing on this. Expect a quiz next week. Do we have time? No, never mind. We don't have time for a quiz. But just come to office hours if you have questions. So you've got all of this. This is due Monday midnight for you guys. Monday midnight? Sunday midnight for you guys. So so get it done, all right? All right, you're free. You're all free. Have a good day, and I will talk to you all later. Come to office hours with questions. Bye, guys.
Thank you, Miss Crockett. See you.
See you later.